Hey, good afternoon. Let's just give a minute or so for people to join in.
Okay.
All right, we'll get started now. Good afternoon. Welcome to this month's edition of the, okay, let me go back to the introductory screen actually. So welcome to this month's edition of the webinar series on applied analytics success stories. My name is Rajesh Tyagi and I'm the host for this webinar series. So this series is an initiative of the Informs Practice section. So before we get started, let me just spend a couple of minutes talking about the Informs Practice section. So the objective of this section is to advance the practice of analytics, operations research, and management science. And to that goal, it conducts a number of activities. Of course, we have the three annual competitions, the Ehrman Award, the Wagner Prize, and the George Smith competition. We also have monthly webinars or bi-monthly. So the first one, and these are the ones with the red font towards the end. So we have the Applied Analytics Success Stories, which is this particular webinar. This one focuses where I guess our speakers talk about problems they have encountered and solved. We have another series called Outstanding Analytics Organization Webinars. This one focuses on the analytics organizations, how they are set up, what kind of projects they work on, what kind of teams they have, what are the skills they are looking for. And these two webinars, the success stories and the analytics organizations, they alternate every month. So next month we will have the analytics organization webinar. And each month we also have a monthly virtual networking happy hour. This takes place on the last Friday, so it'll be February 25th. And again, for all these, you can go to the practice section website and register for those webinars. Just want to, again, if you like this webinar, the one we are going to have today, and we have an excellent one in store for you, we hope you will consider joining this section on practice. With that said, let's talk a little bit about today's application, today's webinar. So the topic for today is operations optimization applications at General Electric. And we are pleased to have Dr. Srinivas Bollapragada, who is a chief engineer in operations research, AI, and analytics at GE Global Research Center. So let me give a very brief introduction to Srinivas. So Srinivas is a chief engineer specializing in OR, artificial intelligence analytics at General Electric's Global Research Center in Niskayuna, New York. His research interests are in business applications of planning, optimization, and AI technologies. During the past 26 years at GE Research, Srinivas has led the development of numerous innovative algorithms and decision support systems that are in use at several GE businesses and their customers. Some of his accomplishments include the movement planner algorithm for dispatching trains, the yard planner algorithm for building trains, algorithms for sourcing and delivering wind turbine towers and blades to wind farm sites, managing intermodal rail terminals, selling and scheduling television commercials, managing contractual service agreements, recovering airline schedules from disruptions, optimizing service operations, computing optimal inventory levels, improving hospital operations, optimizing financial portfolios, and supporting investment decisions. Srinivas has published over 30 articles in journals such as Operations Research, Interfaces, European Journal of Operational Research, IIE Transactions, and Production and Operations Management. Srinivas has a PhD in operations management from Carnegie Mellon University and master's and bachelor's degrees in electrical engineering from Indian Institute of Science in Bangalore and Indian Institute of Technology in Madras, respectively. He is the recipient of several awards, including the Edelman, Wagner, and Nicholson Finalist Awards, IIE Transactions Best Paper Award, GE's Idlecheck and Blodgett Awards for Technical Excellence, and the Dushman Award for Team Leadership. He has served as Editor-in-Chief of Interfaces, Chairman of the Edelman Award Committee, the Area Editor of OR Practice, and President of Informs Practice Section. He was named an Informs Fellow in 2009. Quick note before we get started. The Q&A session will be at the end of the webinar. So during the webinar, feel free to type in your questions. You'll see a Q&A button at the bottom of your Zoom, interface. Just click that button, type in your questions. Towards the end, Srinivas will answer those questions. And if those questions continue overflow after 1 o'clock, we will continue till 1:30 as necessary. With that said, I'm very pleased to have you, Srinivas. Please go ahead. I'm going to stop sharing my screen. Okay. We can see your screen.
Yeah.
Yes.
Okay. Thank you, Rajesh, for the introduction. As Rajesh said, I've been with GE for 26 years. And during this time, I had the opportunity to develop solutions for many complex operations optimization problems facing the company and its customers. I'll share some of that work now. Because GE had businesses in many industries, my work spanned a wide range of domains, including aviation, energy, healthcare, finance, broadcasting, plastics, and space. I was able to publish about 30 to 40% of my work over the last 2 decades. I'll present some of that work that is already in the public domain. I'll be covering this work at a high level. In most cases, I will provide references to my published work. If you would like to learn more about the work, please refer to those papers. Let us begin with the aviation industry. The goal of the work described on this slide is to minimize the total cost incurred on a flight. An airline incurs 2 primary variable costs on a flight: time cost and fuel cost. Time cost is a nonlinear cost that an aircraft incurs if it does not arrive at its destination airport at the scheduled time. The amount of fuel consumed depends on wind speeds, wind directions, and atmospheric temperatures encountered during the flight. An aircraft's airspeed and cruise altitudes also have a major impact on the fuel it consumes. We developed a novel approximate dynamic programming algorithm that determines the optimal airspeed and cruise altitude during various segments of the flight to minimize the sum of fuel and time costs. The output of this algorithm is entered into the flight management system in the cockpit, which in turn, and this flight management system flies the plane by controlling the autopilot system. More information about this work is available in a paper that we had published in Interfaces in 2013. The reference is mentioned at the bottom of the slide. Airlines face disruptions to their published schedules daily due to many reasons, including airspace congestion, unplanned maintenance, weather, and security related issues. These disruptions are usually known with little lead times, leading to flight delays, cancellations, delayed flights, and crew and passenger misconnections. US airlines incur over $25 billion in costs annually due to schedule disruptions. When disruptions occur, most airlines currently make changes to their schedules manually in a three-step process called schedule recovery. In the first step called ops recovery, they delay and cancel flights and reroute aircraft to meet the constraints imposed by the disruption. In the second step called crew recovery, crews are reassigned to rescheduled flights by rerouting regularly scheduled crews and calling on reserve crews as needed to minimize crew costs. Finally, in the third step, passengers on canceled and delayed flights are rerouted to minimize passenger discomfort and airline costs. Each of the three subproblems is very complex to solve by itself. So, owing to their complexity, most previous attempts mainly focused on solving each of these three subproblems independently. However, solving the subproblems sequentially leads to multiple issues that require significant human intervention. For example, the output of the ops recovery model may be suboptimal or even infeasible for the crew problem. It can require multiple manual iterations between the first two subproblems to generate a solution that is both ops and crew feasible. Moreover, since passenger connections are typically not considered while solving the aircraft and crew problems, the resulting solution may lead to excessive passenger delays. We developed a holistic schedule recovery algorithm that simultaneously solves the crew and the ops and crew problems iteratively without manual intervention. Our algorithm begins by solving the ops and crew problems sequentially. If there are uncovered flights, it uses an optimization algorithm to determine the minimal delays and cancellations that are needed to staff the uncovered flights using reserve or standby crews. It then resolves the ops and crew recovery problems after delaying and canceling the flights as recommended by this optimization model. It repeats this process until a schedule that is both ops and crew feasible is achieved. Finally, once a good schedule that is both ops and crew feasible is achieved, the passenger problem is solved to reroute the passengers on canceled flights. Let's move on to the next topic. Airlines invest hundreds of millions of dollars in emergency spare parts inventory. These spare parts are used for unplanned maintenance and are stored across a number of bases in the airline's network. When an aircraft needs a part, it must be supplied as soon as possible. Otherwise, the aircraft is grounded until the part is available and the repair is completed. The failed part that comes off the aircraft can be reused after repair. We developed an algorithm to minimize the spare parts inventory needed while meeting the service level requirements of the airline. In addition to computing the optimal inventory levels by location for the thousands of SKUs of spare parts that they stock, the algorithm also computes important metrics such as flight delays and cancellations that are caused due to spare parts shortages. I have done a lot of work to improve the operations of the rail industry. The algorithms that we have developed are in use at multiple railroads across the world. I'll share information on two of those algorithms. The first is called the movement planner, which dispatches trains in real time to increase the throughput of the rail network. A Class 1 railroad in North America, such as Norfolk Southern, owns more than 20,000 miles of track and runs over 2,000 trains a day. These trains are controlled by dispatchers from centralized dispatch centers. The average speed of freight trains in North America is around 20 miles per hour. This is because trains end up waiting for hours at meet and pass locations where two trains need to get past each other on a single track. So they have one of the trains is placed in a siding and the other train goes by. If we can increase the average speed of trains by 1 mile per hour by efficiently scheduling the meets and passes, we can save a Class 1 railroad like Norfolk Southern $200 million a year. We have developed such an algorithm which generates a detailed plan for moving trains on the rail network for the next 8 hours. We implemented it in a movement planner system, which is currently in use at multiple railroads across the world. This system generates a plan for the railroad every 2 minutes and uses it to auto-route the trains by controlling the signals along the track. This work was a finalist for the Riemann Award in 2016. More information about it can be found in the reference paper shown here. The next topic I want to discuss in the rail industry is the yard planner system that we have developed. This system optimally manages rail yards to increase their throughput. In a rail yard, incoming freight trains bring rail cars that need to go to different destinations. Those trains are disassembled and their cars are sorted by their destination codes and are then used to build new freight trains that travel to various locations. A series of operations are used to achieve this. Incoming trains are received onto receiving tracks. They are then inspected and their rail cars are sorted by their destination codes into classification tracks. The sorted cars are then pulled into the departure tracks. The departure trains are then built, tested, and departed. Many operational decisions to manage the yard are made locally and manually, and this leads to suboptimality in the way the yard is run. On an average, rail cars spend over 60% of the time sitting in rail yards and less than 40% of the time traveling on the railroad. Reducing the amount of time that rail cars spend in yards leads to major savings for railroads. We developed an algorithm and implemented it to improve the operations of the rail yard. This algorithm comes up with a detailed plan for executing all the operations in the yard in real time to make sure all cars are put on the right trains that they need to be connected to, thereby minimizing the dwell time of the rail cars. Let us now discuss a few applications from the finance industry. Large insurance companies have billions of dollars in assets that are generated from insurance premiums paid by policyholders. The assets are mainly invested in corporate and government bonds in accordance with the regulations on the insurance industry. The liabilities are future cash payments to their policyholders. The difference between assets and liabilities is called the surplus. The value of assets and liabilities change with changes in risk factors such as interest rates. But if we match the characteristics of the assets with those of the liabilities, as shown in the second figure, the surplus becomes insensitive to the change in risk factors. The goals of portfolio managers are to maximize return and minimize risk while ensuring that asset and liability characteristics are properly matched. The asset liability portfolio optimization problem can be formulated as a nonlinear program. The objective is to maximize the portfolio return, which is a weighted sum of the returns of individual assets in the portfolio. The risk constraint limits the portfolio risk to be below a certain target value and is nonlinear. All other constraints in the math program are linear. Solving this nonlinear program for different values of the target risk level, we can generate the portfolio's efficient frontier, which gives the maximum return for a given level of risk. The portfolio manager can then chooses the point on the efficient frontier based on the risk appetite of the business. For real world problems with tens of thousands of assets, generating the portfolio efficient frontier was not practical using the existing solvers. We therefore developed and patented a novel algorithm which generates the efficient frontier within a few minutes. Our algorithm begins by eliminating the nonlinear risk constraint and solving the resulting linear program. Since the risk is not constrained in this linear program, because we have eliminated the risk constraint, we obtain the portfolio with the highest return and risk values, which is basically the rightmost point on the efficient frontier. We then successively generate the other points in the efficient frontier, each with a smaller amount of risk than the previously generated portfolio. This is done by limiting risk through the addition of a linear constraint at each step, thereby ensuring that the math program remains a linear program. The linear constraint that we add is parallel to the tangent of the risk function that passes through the previously obtained portfolio. This algorithm generates efficient frontiers for real-world problems with tens of thousands of assets within minutes, because it involves solving a series of just linear programs. This work was also a finalist for the Wagner Prize and is described in more detail in the reference paper shown here. Okay, this slide describes the work that we had for GE, the work that we had done for GE's energy rentals business, which rents power generation equipment for temporary use. Many customers request trade credit. The business was growing rapidly, and manual credit decisions were a bottleneck. We developed a model to make credit decisions automatically using data from Dun & Bradstreet Credit Bureau and the historical data that we had on the customer. We implemented the model in a web-based system that was used by the sales personnel to make most of the credit decisions. This work was also a finalist for the Wagner Prize, and the paper listed here describes that work in more detail. Okay, this was one of my first projects at GE. When credit card holders do not pay their bills on time, the business calls them using automated dialers to request payment. The goal of this project was to maximize right party contact rates by optimally scheduling collection calls. To maximize the expected contact rate, right party contact rates. Our algorithm maintained probabilities of contacting each customer by the hour of the day and day of the week, and the calls are scheduled to maximize the expected number of contacts while meeting the capacity constraints of the call center. Every evening, the algorithm used the results of the calls made during the day to better learn the contact probabilities of each customer. This work is published in Production and Operations Management Journal in 2010. Let us now discuss a few applications from the television industry. TV networks in the US sell around 80% of their airtime inventory during the upfront market, which is a brief period that starts at the end of May. During this time, clients approach NBC with sales requests to purchase time for the entire year. In response to the client request, the TV network develops a detailed schedule of commercial slots to meet the requirements of the client. Prior to this work, NBC generated sales plans manually. These manual sales plans took about four hours to generate. Moreover, there was a lot of rework because plans did not meet the goals of pricing managers at the network or the client requirements at the first attempt. We developed an algorithm to automatically generate new near optimal sales plans and implemented it in a system that was used across NBC. The system decreased the sales plan generation time by 90%, decreased rework by 80%, and increased revenues by tens of millions of dollars. This work was a finalist for 2001 Edelman Award, and the reference is at the bottom of the slide. Networks sell commercials by the air date and show on which they air. The exact location of the commercial within the show is determined at a later stage, usually close to the air date of the show. There are many criteria the networks must meet in scheduling commercials in a show. The schedule should be such that no two commercials promoting competing products from different clients air in the same break. The audience ratings tend to be higher at the start and end of a commercial break than during the middle of the break. Therefore, advertisers generally prefer the first and last positions in a commercial segment to those in the middle. TV networks normally promise their clients an equitable rotation of commercials among the various positions within a commercial break. In the example shown here, In the initial schedule, there are 3 product conflicts in the first 2 commercial breaks, and those conflicts are highlighted in red. Here there are 2 auto commercials and 2 beverage commercials are competing against each other and they are scheduled in the same break. But after rearrangement of commercials on the show, all the conflicts are resolved. Now, this rescheduling of commercials on shows was done manually and is cumbersome, time intensive, and error prone. We developed and implemented an algorithm that automated this process. In addition to reducing the back office, our work increased customer satisfaction by minimizing errors in meeting customer requirements. We published this work in Operations Research. A couple of years back, I noticed that this paper was highlighted on the journal's website as one of its 6 most read papers. I've done a lot of other work in the television industry. 3 other projects are shown here. The first one describes our work in scheduling commercial videos. Major advertisers each purchase many slots to air commercials on a broadcast network. They have multiple commercial videos to air in those slots, and they typically want the airings of a video to be as evenly spaced as possible. So our objective is to schedule a set of commercials in a set of available slots such that multiple airings of the same commercial are as evenly spaced as possible. We present multiple approaches to solving the scheduling problem in a paper that we published in Operations Research in 2004. The second work shown here is published in Interfaces in 2008 and describes a novel algorithm that we had developed using a combination of Delphi method and grassroots forecasting to predict upfront market demand for TV networks. The third one shown here describes models to determine the fraction of inventory that should be sold in the upfront market. As I mentioned earlier, networks sell 80% of their inventory in the upfront market, roughly around 80%. And then this happens before the season begins. And the remaining inventory is sold during the scatter market, which occurs throughout the year. The scatter market prices are in general higher than the upfront market prices by around 15% or so. However, if too much inventory is saved for the scatter market and the demand realized is not high enough, the prices during the scatter market may go up. This paper analyzes this problem and provides a methodology to help networks plan their upfront market strategy. This work was published in IIE Transactions in 2008 and won the journal's Best Paper Award that year. Let us now discuss a few applications from the energy industry. GE Power has long-term service agreements with customers to service their gas turbines. Revenues on these contracts are negotiated at the start of the contract. Therefore, minimizing the cost of operations is the main way to increase net income realized from these contracts. The service costs and parts inventory costs can be minimized by optimally scheduling the planned inspection events. If inspections of 2 turbines at different locations are staggered we can repair the parts from the first turbine and reuse them in the second turbine. This allows us to carry only one set of parts in inventory instead of two sets to service these two gas turbines, thereby reducing the capital that is tied up in inventory. Prior to this work, long-term service agreement modelers manually schedule maintenance events and made part flow decisions for each gas turbine. This was a cumbersome process which required many hours of modeler's time per contract. Moreover, since scheduling decisions are complex, it was not always possible for a modeler to arrive at the optimal solution. We developed a novel algorithm that can automatically generate optimal plans within a couple of minutes of runtime. The business has been using this algorithm since 2015. An earlier version of this work is discussed in the paper shown here, and this paper is published in the European Journal of Operational Research. After the completion of this project, we developed a field engineer scheduling algorithm that optimally assigns hundreds of field engineers to service the gas turbines during these maintenance outage events. During a maintenance outage, multiple tasks are performed on the gas turbines and other equipment in the power plant. Each task requires field engineers and technicians with specific skill sets and experience levels. These field engineers are located across the world with limitations on the countries that they can travel to and restrictions on their availability due to training schedules and vacation plans. We have developed the field resource optimizer product to optimally assign hundreds of field engineers to thousands of tasks over a year to minimize the total cost of field service operations while meeting all real-world constraints. The algorithm is used to assign field engineers for the entire year and then reassign them as needed daily based on any changes to the schedule that might arise. This work was a finalist for the Euro Practice Award and a semi-finalist for the Edelman Award in 2021. This slide describes our work on predicting demand for utility scale energy renewable energy power plants. This work was done in 2008. At that time, renewable energy was still much more expensive than conventional energy. And the main driver for demand for utility scale renewable power plants are the renewable portfolio standards or RPS requirements. So these standards, which vary by state, require utilities to use renewable energy to meet a certain fraction of their electricity demand. Failure to do so requires them to purchase renewable energy credits or RECs from entities generating surplus renewable energy beyond their RPS needs, or pay a penalty that is proportional to the shortfall in meeting their requirements. Since the main driver for the adoption of renewable energy technologies are RPS requirements, our approach to forecasting the demand for utility scale renewable technologies in the US is to determine the renewable energy plants to be built across the US to minimize the cost of meeting RPS mandates. And then we did this using a math programming model. The objective is to minimize the cost of meeting the RPS requirements over a decade. The first set of constraints here ensure that the RPS requirements are met. The rest of the constraints model the transmission capacity and other capacity constraints in the system. The mathematical program formulation, it turns out to be, it's very large and it turns out to be difficult to solve using existing solvers. So we developed a fast heuristic which generates near optimal solutions within minutes. In addition to forecasting the plants to be built by a state by renewable technology, the algorithm also computes long-term average REC prices. These are the prices for the renewable energy credits using marginal cost analysis. We implemented this algorithm in an easy-to-use tool, which is used for renewable energy project evaluations, forecasting demand to better plan manufacturing capacity, and evaluating the effectiveness of government policies on and for advocating for more effective policies. We published a paper based on this work in Interfaces in 2013. The objective of this work is to develop and implement a model that predicts the solar demand by year, state, and market type across the US for over a decade. We used market penetration and technology adoption models from the marketing literature to forecast this demand. In the interest of time, I will skip discussing this work, but please refer to the paper at the bottom of the slide if you're interested in learning more about it. This work was also a finalist for the Wagner Prize. In the rest of my talk, I will cover one application each from healthcare, additive manufacturing, and satellite industries. In the for hospitals, bed management is an important function and has a big impact on patient care, patient flow, and hospitals' operating margin. Many requirements need to be met in assigning patients to beds. Depending on the clinical specialty, different types of beds are preferred. There are also non-clinical requirements. For example, some patients may prefer private rooms, and also in a shared room, we must place patients of the same gender. We developed and implemented an algorithm to automatically assign beds to patients who are waiting in various areas of the hospital. When we implemented and tested this at the Mount Sinai Hospital, the patient wait times had significantly decreased. This work is also a finalist for the Wagner Prize, and and the reference here actually has more details about the work. 3D printing or additive manufacturing has been gaining wide acceptance. For example, GE's aviation business now manufactures several aircraft engine parts using 3D printing. The newer 3D printing machines have multiple lasers working simultaneously on the build plate. The throughput of a 3D printer can be improved by equally allocating work to all the lasers. So if you load balance if you do load balancing across the lasers, all the lasers are busy pretty much all the time, and that increases the throughput of the 3D printer. But while doing so, we should be careful to ensure that a laser's assigned work area is not occluded by the smoke generated by other lasers that are also working simultaneously. We used a construction heuristic and a local search algorithm to solve this problem. And our solution is described in a forthcoming paper in Interfaces. I'll end the talk with this application from the satellite industry. This is a joint work with Rajesh Tyagi, the host of this webinar series. We did this work for Americom, which is a satellite communications services provider that was owned by GE. Its customers included broadcast and cable networks, internet service providers, and various news organizations. Its AMC-12 satellite has 24 transponders and can simultaneously serve 21 different markets covering North America, South America, and Europe. Each transponder can be set to one of 8 possible configurations. The capacity of the satellite by market can be controlled by setting these transponders. So we developed an algorithm to optimally set these transponders to maximize revenues. So this work is described in our Wagner finalist paper that was published in Interfaces. I will conclude my talk here and take any questions.
Hey, Srinivas, if you can click on the Q&A button, there are a couple of questions there. And Beth, if you can open this to all the attendees so they can ask questions directly as well. Yeah.
Okay. Yeah, I can see the questions actually. There are 2 questions. I mean, one from Irv Lustig and one from John Mel. Are those the only ones you see, Rajesh?
Yeah.
Okay. Irv's question is, how does the solution for airline schedule recovery compare to the work that Continental Airlines did about 20 years ago that won the Edelman? Okay, this is a good question actually. So this, the company that did this work for work for Continental Airlines 20 years back, that is actually acquired by GE, and now it is part of GE's digital business. In fact, actually, that company had solutions to, there are 3 sub-problems that I talked about: the ops recovery, crew recovery, and passenger recovery. So that company, when we acquired them, had solution to the first 2, the ops recovery problem and the crew recovery problem. But they were basically 2 independent problems. And the Continental work that Irv is talking about here is basically a solution to the crew recovery problem. So, like I said before, I mean, most of the solutions that are there in the literature, they basically solve these sub problems independently. And the solution that that we have come up with is basically to holistically solve this problem, all the 3 problems together. And let me go to the next question. This is from John Mill. What are the challenges of getting acceptance of your model from users, management, and executives, and tactics to conquer those challenges? Yeah, there are always challenges to get acceptance, but from in my experience, I found that whenever if you listen to the users and understand exactly what they want and deliver what they want, I think after that, I mean, everything else is easy. I mean, there are definitely the start of the projects, there are challenges, especially when you're working with a new customer. People are skeptical. But then once you have a first success, then it is pretty easy. Like for example, I can give you an example about I can talk about my NBC work, which was one of the first things that I did. When I came to GE, the very first time that I wanted to do some work for NBC, it was very challenging. I mean, they didn't believe that that could be done. This was the sales planning problem. But I had a small amount of funding, internal funding, which I used to solve the problem partially. And after that, this person that I was working with was completely convinced. And then, what I find is that when the final user is convinced and he believes in you, and everything else will fall in place. You can get the executives, or you can convince the management, the executives, and everybody else. So it's from that has been my experience. I mean, it's if you can convince if you can show the final user that whatever you deliver is going to be of use to him or her, everything else is all the other things can be overcome pretty easily. I mean, it's the main thing is basically you need to make sure that you need to understand who the final user is, and what are the requirements, and then make sure that if you can convince them that you can deliver that, then you would get support. I mean, that's basically has been my experience. Let's move on to the next one.
Hey, Srinivas, one question, if I can, before you go to the other question, sort of somewhat related to John's question. So, I mean, the GE Research is more of a separate entity. It's a part of the corporate group. And we have, of course, all the GE businesses in a way are distinct from that perspective. So can you talk a little bit about how these projects get initiated? How does the business come to you, or you take ideas to the business, and where does that interaction, or when does that interaction take place? Can you maybe perhaps talk a little bit about that?
Yeah, sure, Rajesh. There are multiple ways projects are initiated here at GE Research. There are both formal and informal ways. We have multiple day technology sessions with the businesses during late summer and early fall, when many people from the businesses, including their CEOs, visit the research center. They describe the problems they are facing to us, and then work with us to define projects for the next calendar year. So that is called a session T, and that is one formal way that this happens. And GE Research also has business liaisons called business program managers, one for each business. And their job is to learn about the business issues and connect researchers with the people in the business to solve those issues. And thirdly, there is this informal way, where researchers actually reach out to people in the business with their ideas and get their projects funded. In my case, actually, most of the projects are a majority of my projects basically came through this informal route. But I mean, there are but at the research center, the majority of the projects are actually they come through these formal routes that I had described earlier.
Thank you. There are a couple of questions in the Q&A, and there are a couple of in the chat, and I'll try to dig those out. If you can answer the ones in the Q&A, please.
Okay. Then next question I see there is from Michelle Fisher. You describe an incredible variety of work. Do you consider yourself a generalist or a specialist in the application of work to real-world problems? Well, I like working on real-world problems, and my training is in operations research. and AI. I would like to find the and also I like to learn new techniques as well. So I like to use the best technique that is available to solve the problem at hand. Sometimes the techniques that I learned in school are not sufficient for that. Like, for example, one of the projects that I skipped through it. I talked very briefly about it. It's the one on predicting solar demand. That work is mostly based on the techniques that I used in solving that that problem. We're mostly from the marketing literature. So yeah, I mean, for me, it's my training. Like I said, my training is in OR, but but my interest is in solving real world problems. I hope I answered that question. The next question is also from Michelle Fisher. Can you comment on the impact that informs practice programs and prizes have had on your work? The prizes are a way of publicizing our work. I don't know if they had a lot of impact on the work itself, but they definitely gave me a conduit to publicize the work, and I really appreciated that. Let's go to the next one.
Yeah. Just if I can answer that one from Michael Blazer. Yes, we will be. This video is going to be recorded and then posted, and you will find a link if you go back to the practice section website, and there is a menu item for past webinars, and I think by next week or so, a copy of this webinar should be posted there. Continue, Srinivas.
Okay, the next question is from Murali S. In your portfolio optimization work, how valid will your methodology be if market risk profiles of assets and liabilities differ? Yeah, actually, this is the algorithm that we developed is a general algorithm for solving a portfolio optimization problem. The way we handle those the matching constraints, they're all linear constraints actually, and so if the risk profiles differ, you can never match them exactly. So what they do is the way you match those risk the risk profiles is basically what you have is you have these assets have what is called duration and convexity, and duration is basically, I believe, the first derivative, and convexity is the second derivative of the of the variation of that asset with respect to the risk variable, risk factor. And what we do here is you basically set the durations and the duration of the portfolio, the duration of the assets, the net duration of the assets. You set that, make that equal to the duration of the liabilities. That's how you solve it. But it is a general optimization, a general methodology for solving any portfolio optimization problem. It is not just restricted to solving an asset liability portfolio optimization problem. I'm not sure if I've fully answered that, but I will just move on to the next question in the interest of time. The next question is from Sharon Arroyo. What was the most technically challenging problem you solved? Okay, I think the most technically challenging problem was, I believe, was the movement planner. because that problem was unsolved for many years. I believe it was unsolved for like 30 years before it was. And in fact, actually, when I started working on the project, there is this division at transportation was already working on it for 13 years, and then they could not solve the problem. And in fact, actually, there were two other companies also, two other big companies also were trying to solve the problem, and they spent 15 years solving that. And then both of them actually had solutions which did not work. And I know that because they have implemented those solutions at railroads, at different railroads, and all of them didn't work. And all these railroad companies, they've tried to use it for a couple of years, and then finally they gave up. And that problem is very complex. I mean, it is you have to come up with a solution for a problem where there are 20,000 miles of track and 2,000 trains, and all of that you have to do it within 2 minutes. And the reason is because things change dynamically on the railroad, and you're actually controlling the signals along the track in real time. And to solve such a problem, such a hard problem in such a short amount of time, in real time, basically, is very hard. So that was that I believe is one of the hardest problems I solved. In fact, actually, this airline scheduling problem also is very hard. But I think that is the one. Yeah, there are a few other problems which are also. Yeah, but I think I'll just say that. Yeah, that is probably the hardest problem I solved. The movement planner problem.
Yeah, so there was one question from Pooja. Pooja Devan had, I think she posted on the chat, so you probably can't see it, but I'll read it out for you. Following up on John's question, and this was John's question about, how do you sell this idea, to the management and so on. What's usually harder, the change management and adoption by the business, or the technical solution?
It depends on the problem, actually. For example, I talked about movement planner. Everybody knew that they needed a solution for that, and so it's so there. The question was, there was no solution out there. That was a technical problem. It was people could not solve it. So there, solving the technical problem was the hardest part, because everybody else was convinced that if you had this solution, it'll save a lot of money. And in some other cases, in some situations, change management could be harder. Depending on the problem. The problem might be easy to solve, but maybe getting it implemented might be difficult. It varies, actually. I think it varies by the problem. But on the change management, I have seen, this is what I've seen, like I said before, if you can convince the ultimate users to use your product, everything else basically falls into place. That's what has been my experience.
All right, anybody else has any questions? I think we all can speak now, I guess. So if you have any questions you want to ask, please go ahead. Okay. All right, maybe that's it. Hey, Srinivas, really want to appreciate your, oh, hold on. I think Irv has a question.
Yeah, hi, can you hear me now?
Yes, sir.
Yeah, I think you had to raise your hand and unmute. It's not, everybody's not open. So Srinivas, with respect to your last question that Pooja asked, I think the other way of looking at it is in the railroad problem, they had no solution beyond a manual one. So then so the change management wasn't as much because you weren't changing the business process, you were just giving them a better way of doing things. But I imagine like when you did the work for the NBC advertising sales plan generation, you were changing their business process. And that then becomes a lot more challenging because the OR solution is saying to them, hey, not only do we have this great tool that can do things better, but we're going to change totally the way you were working and the way you've been doing things. So You know, because I've worked in that area too, and getting people to think differently, and that then becomes the bigger challenge. So I think your answer is right that it depends on the problem. I think it may more align with what existing solutions are in place and how much the new solution will change the way that they're operating. So it's not a question, it was just a comment in response to what you said.
Oh, okay, yeah, sure, definitely. Yeah, for me, when I first started working with NBC, I was fortunate to, their manager of sales planning was a very smart guy. And when I first met with him, he described, he described how they do their sales planning. And after I heard him what he's, after he heard me what after I heard what he said, I basically told him that I can come up with a solution that can automatically do this. And then he did not believe me. He said, there is no way you can do this. And he had an experience with his IT people. And then he thought it was, I'm coming from the IT side. And he said, I know what these people can do. I mean, I don't believe they can do this. But then I had a conversation with him. But one thing he noticed was that as he was describing the problem, I was understanding everything he was saying. And then at the end of that, he just stopped and told me, it's, when I describe this when I train new people, when I train these new planners who come to work for me, it takes me so much time to get these concepts across. And then you're getting this so fast. I'm going to work with you. That's what he said. I don't believe you can do this, but you seem, I see that you understand these things very fast. So I'll work with you. But then after that, I said, okay, then I went back and then I based on what he said, I put together a small linear program which does a very rough planning. And then when I showed it to him, he was then he realized that this can be done. Though that was not solving the full problem, it was basically solving a made-up toy problem. Then he realized that it could be done. And then after that, he basically said, okay, I'm going to work with you. And so it also depends on you need to find the right users also, I believe. So some people are more receptive than the others. And it's
business sponsor is a big deal. I have a different question.
Yeah.
You've been able to have the time, which I never have, to write papers about your work. Is that just because you're in a research center that is encouraging you to publish about your work and therefore you've given the time to do it? Because I imagine, given your skills and the demand for your services, there's always a new problem that you could be working on as opposed to writing a paper. That's certainly, when a paid consulting business, that's where I live.
Yeah.
So
It's actually, we are not required to write papers, and we are also not really given a lot of time to write papers. I do it because I like to do it, and some of us do it actually. Not everybody does it. There are some of us who like writing papers, and there are very few of us actually. And I like to do that, and I so in the long run, it's we are not evaluated based on the papers we write, but in the long run, actually, it helps. It's we also have we also get promoted here and things like that. And then when you are getting promoted, those things like that matter. But otherwise, it's most people who do it on their own time. And also, when the other thing is, someone asked me about these awards and prizes. So when you apply to this award, you are forced to write a paper. So that's another way to write a paper.
This session is open to all. If anybody else has any questions. Okay. Again, this is being video recorded and should be posted sometime, hopefully by next week or so. In the meantime, again, Srinivas, that was some wonderful presentation, a lot of new exciting projects there, cutting across many industries. Really appreciate you taking time to talk to us about your work.
Okay. Thanks, Rajesh. Thanks for inviting me.
All right. Again, I want to thank the audience also for dialing in. And again, if you like these webinars, go to the practice section homepage and look what the upcoming webinars are and sign up for them. We typically have them every month. So thank you again for participating, all of you. Have a good day. Thank you. Bye.
Okay, thanks. Bye.